All right, so we're going to be evaluating and graphing piecewise functions today, and a piecewise function is a very strange looking function. It has at least two parts, sometimes three for Algebra 2 students, and depending on what part of your domain you're in, will change which part of the function you're looking at. So if you do have two colors, this is a great time to use them. So with my first color, I'm going to box in the first piece of the piecewise function, which is the recipe 3x minus 1. But notice right next to that function it says if x is less than or equal to 4. So you're only supposed to use this blue function if your x's are less than or equal to 4. So like for instance, if you have x equals 3 or x equals 2 or x equals 0, you'd be using that blue function. And then with my second color, if you have one, let's box in that second function piece. That piece is recipe 2 times x plus 7. And you're only going to use it if your x's are greater than 4. Yes? Right. Yes. So in that case, if you get exactly 4, which I think we're going to run into in a minute, we got to make sure we use the proper piece of the function. Very good. So what we're going to do first is we're going to evaluate this piecewise function at specific x values. And the first question says f of 10. That's function notation, and it's a very fancy way of saying please plug in x equals 10. So my question to you is, should I be using the blue function or should I be using the red function if x equals 10? The red function, tell me why. Because 10 is greater than 4. So using our red function and then plugging in x equals 10, you get 27. There you go. So then back to his question earlier, he said, what about exactly x equals 4? So read carefully, which function are we supposed to use when x exactly equals 4? The blue function. So 3 times 4 minus 1 would be 12 minus 1, which is 11. Very good. Okay, what about if x equals negative 2? Okay, so that top function, that blue function again, because negative 2 is surely less than 4. So 3 times negative 2 minus 1. So negative 6 minus 1, yes, negative 7. And then it wouldn't be Algebra 2 if we didn't throw a fraction at you once in a while. What's 5 halves as a decimal? Yeah, 5 halves is also 2.5. Sometimes decimals are easier to look at when we're evaluating. So would that fall under the blue function or the red function if it's x equals 2.5? The blue function again. So 3 times this time 2.5 minus 1. It's like 7, what? It's something. Minus 1. 6.5, there we go, 6.5. Very good. So notice, for each one of those questions, I only gave you one answer for a correct answer. Sometimes kids get confused and they plug x equals 10 into both pieces of the function and then they write down both answers. And I can't accept that as an answer because that tells me you don't really understand what a piecewise function means. So make sure when we're evaluating a piecewise function, you're only looking at the correct part of the function depending on which domain you are in. So, a couple more of these. Now be careful, there's a lot of problems here kind of thrown into one section, and this whole top row is function f. So you're going to be looking over here at function f. Now before we start evaluating, function f is very strange. The first piece of the piecewise function is 3. And then the second piece of the piecewise function is just 2. These are what are called constant functions. They're very boring because they literally just give you a horizontal line at 3 and a horizontal line at 2. So when it comes to evaluating a constant function, I think they sometimes confuse kids because they're so simple. Any time you go to use this blue function, the answer is going to come out to 3 every single time. So anytime you use the red function, the answer is going to come out to 2. So we have to make sure we're using the appropriate function here, guys. What if I'm plugging in x equals 2? It says use this function if your x's are less than or equal to 0. Use this function if your x is greater than 0. Which one are we? We're greater than 0, so what's our answer? 2. Very good. Okay, number 2 right next to it here. It says go ahead and evaluate that function at -4. So does that fall under the less than 0 or the greater than 0 category? Less than 0. Yes, so the answer is just 3. How about exactly 0 this time? Well, this is the great debate. Are we using the top function or the bottom function when x is exactly 2? Or 0, excuse me. Top function, very good. See that equal to sign? It only exists on that top piece of the function. So this is the only function you get to use when you're 0. So the answer is coming out to 3. Well, 6 is a different function. Be careful, it's g. Yeah, that's okay. We'll get to there. All right, and then function f evaluated at 1/2. So when x equals 1/2, is that less than 0 or greater than 0? That's greater than 0, so going to that function, I get a 2. Very good. So constant functions, while they are weird, they are horribly easy to evaluate. For the sake of space, do you guys mind if we just scribble out g? There's just a lot of stuff going on here. Let's look at function h. So you guys are only looking right now at function h. So if you have 2 colors, let's use them. Oh man, does that say 1/2 x plus, or sorry, -4? I hope so. And then this says 3 minus 2x. And we're going to use that top function if your x's are less than or equal to -2. And we're going to use the bottom function if your x is greater than -2. So watch which part of the domain we're in when we ask these questions. So this first one, number 9. Where should I look if x equals -4? Is that less than or greater than -2? That's less than -2. So you should be looking at this blue function that's on top. And we're going to plug in, this time we do have to do a little math, we're going to plug in -4. So you guys are very welcome to just type this in your calculator in the home screen. I'm going to do a little mental math because it's Friday and let's have fun with that, I guess. All right, here we go. -2 minus 6, -2 minus 4 is -6. Okay, this next question, back to function h. This time I'm plugging in exactly x equals -2. So which function do I use if it's exactly -2? The blue, yes, the top blue one. Very good. I know some of you are using different colors. Sorry, I should just call it the top function. So top function still, we're plugging in a -2 this time, and I get, let's see, that's -1 minus 4. So -1 minus 4 would be a -5. Okay, so now, same function, but this time my x is -1. Should I be looking at the top function or the bottom function if it's -1 for x? Oh, this time our x is greater than -2, so we're going to use the bottom function. So 3 minus 2, and then times the -1. I think that's a +2, so it's 5. And then what if I'm plugging in x equals 6? Oops. We're using top function or bottom function if x equals 6. Yeah, x equals 6 means we're definitely greater than -2. So using our bottom function, 3 minus 2 times 6 is 3 minus 12. So what is that, -9? Y'all trust in my mental math. That's a scary moment. Are we trusting my mental math or are you checking it? You should totally check the math because it's Friday.
But you said it's Friday, so...
Well, I was trying to challenge myself and not be lazy, but maybe this is going to backfire. Remember, we're recording, so you're going to embarrass me on the internet if you're going to show me that I can't add. Alright, so that's one of the skills you're going to have to do, evaluating a piecewise function. Now we're going to graph a piecewise function. So remember how I had you pick up a highlighter? You're going to want to use it here. So same look, we have 2 pieces of our function. I'm going to do the same thing with my colored pens. I'm going to color This one I'll do blue again, and this one I'll do red again. But this time, because we're going to have to visualize this on a graph, I'm going to visualize where my function splits. And that's where the highlighter comes in. So what we're going to call the boundary line is the part in the domain where your function switches from one function to the other function. Anyone identify where that number is? Where does it switch from top function to bottom function based on what x value? 1. Very good. So take your highlighter and draw a highlight line through x equals 1. It's going to autocorrect. Yeah. You know I didn't draw a straight line. That was magic. So that's not part of my function, but what it is it's taking my coordinate plane and it's splitting it into two what we call half planes. So that blue function is going to be on one side of the half plane and the red function is going to be on the other side of the half plane. So this top function, 2x minus 1, it only exists for x's that are less than, ignore the equal to for a minute, less than 1. So which side of my yellow line are we on if it's less than 1? The left side over here. Good. So this blue function, which is y equals 2x minus 1, is going to exist only over here. So I'm going to draw that down at the bottom of my coordinate plane. This is going to be my final check when we get these graphed. These are very arduous problems, so we want to double check as we go. Yes?
How do you know which side to draw?
Say it again.
How do you know which,
Where to draw this? So that has to do with where the function splits in the domain. So whatever this is, that's the highlighter line.
So how would you know?
How do I know that the blue...
So, like, she pointed at the one, right? So if they're going to be the same number most of the time, right?
These will be the same number, yes. So this function only exists for x's that are less than 1. So if I think about my x's that are less than 1, it's all of these x values. So everything on the left side of the boundary line. Okay? Because like -2 would work, -4 would work, -6. Okay. So where would this red function be located? Yeah, everything greater than 1. So on the right side of the boundary line. Very good. So down here I'm going to write down y equals 3x plus 1. That's just going to help me later on when I go to double check that I haven't messed this whole problem up. Okay, there are, and I'm not kidding when I tell you this, like 5 different methods for how to teach this. So Mrs. Meyer and I have been teaching this particular lesson for, gosh, like 8 years now, and together, and for me it's even more than that. And we've kind of nailed down the one method that we feel works best for all kids. But, you know, if you get through this and you're like, you know what, I just do not like this method, I'd like to see one of the other methods, I'm more than happy to show you. You could watch another teacher's video, but like I said, guys, there's like 4, 5, 6 different methods for how to do this. I'm just doing the one that I think works. So here we go. Blue function. We're going to be graphing what's going to be an array. So I need some points. What I'm going to do, using my same blue pen, is I'm going to draw what's called a t-table, like an XY table. And for the blue function, you're only allowed to use numbers for x that are less than or equal to 1. So there's a couple of rules here. You have to start with the boundary line number. So I have to put 1 as my first number. But can you give me 2 more numbers that fit that domain? 0 and -1. Very good. Could you have given me others? -7, yeah. And you don't want to go crazy because we're going to want to fit on the line here. But just anything, any x value less than 1 would work. So guys, in math, when you have an input, which is an x, and you need to find the y, the way you do that is you plug it into the function. So this is where some of us are going to deviate from the process. For me, because I just love mental math, I'm going to do this next step all in my head. So my recipe for y is 2x minus 1. So I'm just going to plug in x equals whatever for each of these ordered pairs. So plugging in a 1, 2 times 1 minus 1 is 1. Plugging in a 0, 2 times 0 minus 1, -1. Plugging in a -1, 2 times -1 minus 1 is -3. Okay, who felt like that was torture? Especially on a Friday. Yeah, You're more than just the 3 people who raised their hand. Here's what you're going to do. Because I always let you guys use calculators, so if you're on a test and you're a little stressed out about this, you're going to make the calculator do all the plugging in. Which is fine. It's going to slow you down a bit, but if it gives you less stress on a test, I'm all for that. So go to y equals, clear out whatever the last kid did, and type in the recipe for what you were just trying to evaluate. I forgot what it was. It was 2 times x minus 1. Thank you. So type it into y1, and then where do I go to see already done table points? Yes, my table. Second graph. And remember how you guys strategically chose the x's already? Just find the ones you want. So -1 pops out a -3, 0 pops out a -1, and 1 pops out a 1. Now why would it be a bad idea for me to keep going down the chart? Ah, the graph stops at 1, remember? X equals 1 was as far as we could go. So don't go crazy. Only pick numbers that are in the right domain. Okay. So for this step, guys, you decide whether you want to manually evaluate it or if you want to use your calculator to evaluate it. All right, guys, let's go plot. That very first ordered pair, do you remember how it said this function is less than or equal to 1? That means that the boundary line point does exist at 1. And you're going to wonder why I'm telling you this, because it's going to matter in a minute. So go ahead and plot a closed circle at 1, 1, which is my boundary line point. I'm using the wrong color. Hello, blue. And then plot points everywhere else you just found. So 0, -1, and -1, -3. And if we did this right, you should be seeing array form. So from the boundary line outwards, draw a ray. Oh, I almost drew a straight line. It's close. You are half done with your piecewise function. Because what's wrong? We still have a whole other piece of the function. Oh boy, here we go. All right, 3x plus 1. Let's talk about that guy. He's going to get his own t-table. But this time, you're only allowed to give me x's that are greater than 1, with one exception. Even though he doesn't exist at 1, you still have to use x equals 1. I'll talk about what we do in a second. That very first point, guys, has to be the boundary line, even if it's an open circle in a minute. Okay, give me your favorite x values that are greater than 1. Don't go crazy. 4. Oh, that might be a little crazy. Go smaller than 4. 3, okay. Give me something smaller than that, then. 2 sounds good. All right. Can't go -2, though. Why? Because I got to stay greater than 1. Yeah. I kept shutting down those big numbers, guys, because, like, first number that got shouted at me was 4, and I kind of looked ahead. Look what's going to happen if you plug in a 4 right here. 3 times 4 plus 1. I'm going to get 13, and then I kind of looked at my graph, and I was like, I don't have 13. I mean, I could fudge it in. It's not the end of the world, but anyways, you guys do need to plug in these numbers, so I'm going to go manually. If you want to use your calculator, that's fine. What you would do is you would change your y1 to your new function, which is 3x plus 1. I think I got this one, though. All right, 3 times 1 plus 1, that's 4. 3 times 3 plus 1 is 10. And then 3 times 2 plus 1 is 7. Okay. Remember how that very first point, you guys were thinking we shouldn't use 1 because it didn't exist, and I said we got to do it anyways? What you're going to do for me on the graph, you're going to note the placement of 1, 4 with an open circle. Anyone want to take a stab at why it's an open circle? Look at this sign here, guys. It doesn't have an equal to bar. Okay, so we're going to draw an open circle at 1, 4. Make it gigantic and exaggerated. I know it's hard to do with pencil. Just do the best you can. Now, off of the boundary line, they're just points. So go ahead and plot 3, 10 and 2, 7. Oh, man. 7. There we go. So, boundary line outwards. Connect and make a ray. Ladies and gentlemen, meet your first piecewise function. Super fun. That took us like 10 minutes, didn't it? They're going to get better. We had to go through a lot of theory and explaining on that question, so it'll get better, I promise. Any questions on why we did something before we move on? Sometimes you need another example before you can even formulate a question. Okay. All right. Start this process again. All right. So we started off with identifying where is my function going to split. So where is the boundary line going to be? At 1 again. They're not always at 1, by the way. It just happens to be at 1 this time. Aw, that's not straight. Okay, try again. I could do better than that. Maybe. Or not. Okay, so there's our boundary line. It's not part of our function, but it's going to help us kind of split. Something weird happens at x equals 1. All right, I'm going to stick with my same colors if you don't mind. Our first function is y equals 1/2 x. It only exists for when x's are less than 1. So that would be over on this side of the half plane. And then our second function is y equals -x plus 3, but it only exists for x's over here on this side of the half plane. Okay. Here's the fun part. We need some points. So I'm going to start with this blue function. And I'm going to want 3 ordered pairs that are chosen very in particular to the domain. You have to start on the boundary line. So I need 1 to be my first x value. Can you please give me 2 more x values that will work for my blue function? Has to be less than 1. 0? Negative what? Negative. Okay, -2 sounds better. Let's go with that. All right. So you either are going to manually plug in all these x values, or you can go to your y1 and change it to a function. Guys, this one's not too bad to plug in. Let's do this, all right? 1/2 times 1 is 1/2. I'm going to write that as 0.5, though. 0 times 1/2 is 0, and 1/2 times -2 is -1. Question, though. When I go to plot this first ordered pair, the boundary line point, am I going to graph an open circle or a closed circle for this blue function? Why is it open? Very good. See right here? It just says less than 1. So at x equals 1, I cannot call it a point. I have to call it an open circle. Oh, good luck here, guys. You got to plot an open circle at 1, 0.5. So it's like in between these two. My rule is, as long as I can tell your circle is open, I realize you're going to have to make it like super large and like not, it doesn't make any sense to have an ordered pair this big. If for some reason you're using pen and you're like, oh snap, that was supposed to be open and I didn't make it open, just circle it and then draw like a little arrow off to the side that says like this is open. And then I'll know on a test that you meant to make that open, because that happens to me a lot. All right, 0, 0 is just a regular old ordered pair. Plot it. And then -2, -1, regular old ordered pair. Plot it. From the boundary line, going outwards, draw me your blue ray. See, that already went faster, didn't it? Already, we're half done. Look at that. Okay, we're going to do the same process this time for the red piece of the piecewise function. So again, you have to use x equals 1 for your first ordered pair. And then after that, it's up to you, but I need you to choose x's that are greater than 1. Don't go crazy. Give me some x's that are greater than 1. 2. Oh, you're getting crazy on me. 4. Oh, very good. Just, you want to avoid going like 28. That would be a silly choice, because while it is true, it's just going to fall off my graph. All right, so here you can either go to your calculator and type it into y1, or you can just think really hard about plugging in all these numbers to your function. Let's see, plugging in a 1 right here. So we got -1 plus 3 is 2. Plugging in a 2, -2 plus 3 is 1. And then plugging in a 4, -4 plus 3 is -1. Question, that very first point, that boundary line point, is it an open circle or a closed circle? Closed this time. Very good. Closed, because it does have that equal to bar. I'll give you a little heads up. For Algebra 2, one of your endpoints will be an open circle and the other one will be a closed circle. Every time.
Every time.
Every time. For Algebra 2, yes.
So every time?
Are you claiming this is the end of your road? All right, here we go. I hope so. 1, 2. Closed circle. And then off the boundary line, they're just points, so you don't have to ask yourself that question. So 2, 1, 4, -1. When you play connect the dots, make sure it's from the boundary line outwards. You're making an array. Ooh, boy. That is beautiful. Now, remember at the very beginning of the problem, I had you guys kind of write down the functions down here? I want you to use your imagination. You don't have to do anything. Just visualize for me. If this blue line kept going, like just a normal line, would I have been graphing the line 1/2 x plus 0? Like, is it a line that goes through the origin and has a slope of up 1 over 2? Yes, it is. But it's only part of the line. It got cut off. And then this red line here, if it continued on forever, would that be the line -x plus 3? So is that a line that has a y-intercept at up 3? Well, visualize it, guys. If you backed up a little bit, would it have crossed at 3? Yeah. Does it have a slope of -1? Sure does. So that's why I like to write the functions at the bottom, because when I'm on a test, because I'm really nervous about this question every time I do it, at the very end I go, okay, this was supposed to be a line with a slope of -1. Did I actually graph that? Because you're going to catch your mistake if you didn't. Yes? All right, let's try this again. See, that one already went faster, right? I mean, it's not your favorite thing to do. What a fun Friday. Super fun. All right, where would your boundary line be in this next example? At 3. Very good. At 3. So draw me a highlighter line at 3. Oh boy, that's not even close to straight. All right. Pretend. I'm going to use the same colors. Now, I feel kind of bad doing this to you because this is the kind of stuff that trips me up as a student and teacher apparently. But that very first function, x plus 2, look what they did here, guys. This exists for x's that are, what is this symbol? That's a greater than. See how they kind of switched it on you? So that's over here. So this side is going to be the y equals x plus 2 function. And then over here is going to be the less than 3, so that'll be the y equals x minus 3 function. They can do that. It's not always in the less than greater than order, so be careful. All right. We're graphing. I'm going to make a t-table for the blue function first. And again, I need you to be careful. You must start on the boundary line, regardless of whether or not it exists. So we're going to have to start with x equals 3. But then remember, you're only allowed to use x's that are greater than 3. So give me your favorite numbers that are greater than 3. Don't go crazy. Okay. What else you got? Okay. Sounds good. So I think this one's pretty good for you guys just to manually plug in the x plus 2, or the x's into the function x plus 2. So we get 3 plus 2, which is 5. 7 plus 2 is 9. And 5 plus 2 is 7. How about that very first point? Because that's the one we always have to worry about. Are we going to be plotting an open circle or a closed circle on the boundary line for my blue function? Open this time because it does not have an equal to. So at 3, 5, open circle. And then everything after that's just a point. So 7, 9, and 5, 7. I don't think I did something right. Are we? No? Oh my gosh, look what I did. plotted at 3, 3 or something. I don't even know what I did. 3, 5. Try again. You notice how I figured out, besides the fact that I knew what the answer was supposed to be, did you see what was going on? My line wasn't going to line up. So that's how I knew something was wrong with at least one of my points. Now it's going to line up beautifully from the boundary line outwards. Oops, I missed. All right, half done. Next function, which is x minus 3. You're only allowed to use that for x's that are less than or equal to 3. So you must start at the boundary line. Give me your favorite numbers after that that are less than 3. 2. Get crazy. What else? -1. All right. Here we go. It is up to you whether you use your brain or your calculator, guys. This one's pretty basic, though. I think you can use the old noggin today. All right, x minus 3. 3 minus 3 would be 0. 2 minus 3 would be -1. And what? -1 minus 3 is, careful, -4. That very first ordered pair, though, the one that's on the boundary line, are we looking at a closed circle or an open circle? Closed this time. Very good. All right, 3, 0. Boom. Closed circle. And then 2, -1 is a point. And -1, -4 is another point. And looking good. I think it's going to make a ray. Here we go. Beautiful. So the rays are going opposite direction of the boundary line. I'm kind of doing a quick double check that the red and the blue formulas kind of match what the graphs look like. They should have the proper slopes and the y-intercepts as a double check, and they do. Notice this blue one, you'd have to extend it down to figure out the y-intercept, but I think he would cross over here at 2. Even on my terrible drawing, I could see it. Yes, sir. You don't have to. I'm trying to give you guys all like the skills to get it right on the test, because every time we test this, kids start freaking out. So I just want you to have a good score on it the first time so we never have to do it again. That'd be great. All right, let's get one more done. Number 16. Well, this is interesting. All right, where's the boundary line? 1. Come on, buddy. So something happened. Oh, man. Something happens at 1. That was supposed to be a straight line. And your first function is incredibly odd. It's one of those weird constant functions. Remember that guy? It only exists for x's that are less than 1, so it's going to be over here on the left side. So the function y equals 2 is just, we're going to see what it looks like in a second. And then your other function, which is y equals 1/2 plus 2, is on the right side of the boundary line. So, same stuff, boundary line, ordered pairs, let's go. You have to start on the boundary line, so you have to try x equals 1. And then for the blue function, you can give me any x values as long as they are, careful, this is a less than 1 again. So give me your favorite x's that are less than 1. Don't go crazy though. 0? Negative? Oh man, -9. Now this is one of those weird constant functions. I'm going to have you, quote, plug in the numbers, but remember when a y equals 2 is your function, there's no work. Just the answer keeps coming out as 2, 2, 2. So all of these ordered pairs are going to have y values of 2. What about that very first ordered pair though, guys? Are we looking at an open circle or a closed circle? Closed. Alrighty, let's plot. 1, 2. 0, 2, and -9, 2. Why would you do that to me? Now I'm going to have to get all the way over there and somehow get a straight line. Okay, you're making an array from the boundary line outwards. Oh man, no chance. Okay, that was supposed to be a straight horizontal line that cut through at y equals 2 the entire time. Whew. Okay, y equals 1/2 x plus 2. That one's going to be a little more typical to what we have been seeing. So you have to start on the boundary line. I don't know why that's getting so crooked. My bad. So x equals 1. Give me any numbers that are greater than 1. You're going to have to hang out for a minute, okay? I'm not ready yet. You're going to have to wait. Okay, so more than 1, 2 works. Anything else? I'm going to go 4. I'll tell you why in a second. Okay. Yeah, the halvesies bother me. I don't like fractions. All right, so plugging in a 1, 1/2 times 1 plus 2 is 2.5. Okay, so we're just plugging into this function. Plugging in a 2, or 2, would be 1/2 times 2 plus 1 would be a 3. And then plugging in a 4 would be 1/2 times 4, which is 2, plus 2 is 4. What about that very first ordered pair, though? Open or close circle? Open this time. Very good. So 1, 2.5. Oh, that's annoying. It's like right above it. And then 2, 3. Oh, no, up here. And then 4, 4. All right, play connect the dots. Lovely. All right, we're going to stop the lesson there.